In this video, we will learn how to insert and delete elements in the linked list, and we'll also think about how we can optimize the operations. All right, let's write a function that can insert a new node at the front of the linked list. In the last video, I talked about how inserting a node at the front can be done in constant time. So when we are implementing insert at front, you don't need any loops, and the process will be pretty simple. The strategy is to create a new node and make it the head, and that's it. The function will be called insert front. The new node would need a value, so the function will have to take in an integer. And we would also need to indicate the linked list by passing in the head. And we don't need to return anything because we are simply inserting a node. So first, let's make a new node and set the value as the input that was passed in. Then we make the next of the new node point to the head. The head, which is now the second node, is already pointing to the next node, so we don't have to do anything about that. And as the last step, we will assign the new node as the head of the linked list. Cool, so that was insert at front. This time we will remove a node with a given value. And if there is more than one node with that value, we will be deleting the node that appears first. The main strategy is similar to the previous operations where we scan through the nodes to find a matching node. One thing that's different about the remove function is that instead of making changes to the current node that has the matching value, we need to make changes to the previous node so that it points to the next node instead of the current node that we're trying to remove. So basically, we are disconnecting the current node from the linked list by making the previous node's next variable point to the node after the current. The function is called remove, and we will take in a head node and the value to remove. Then initialize current by setting it as the head. Let's make a while loop like before and loop it while current is not null. And inside the while loop, we should keep on updating the current node, and this time we will also keep track of the previous node as well by defining a variable previous. You will see why we need that in a second. So we're looping and updating along the linked list, and while we're doing that, let's say that we finally found a match. In that case, we will come out of the loop and modify the next of the previous node to the next of the current node, so we can exclude the current node out of the linked list. And then we will free the disconnected node. Now, can you see why we had to keep track of both the current node and the previous node in the while loop? If we had let go of the previous node when we update current, then we wouldn't be able to access it and modify the next of that node. So we forced ourselves out of the loop when we found a match, but there is also another scenario where we just naturally come out of the loop because there wasn't a match until we arrived to the end. In that case, the current would be empty because that's how we got out of there in the first place. So we are going to put that in an if statement after the loop and before we adjust the pointers. And we're going to say, when we're out of the loop and current is null, finish the whole function. There is one more thing we need to take care of. Right now, we didn't take care of the case where the head itself is the match. We have to handle this case separately because the head wouldn't have a previous node. If this is the first loop, then we didn't assign anything to the previous node yet. So if the head turns out to be the match, we will assign the second node as the new head of the linked list and then free the old head and finish the function. So far, we looked at how we can implement the 4 operations: get item, insert front, search, and remove. Insert front can be done in constant time, but the other 3 operations have linear time complexity. If we compare this to the operations of an array from the past lesson, we can see that insert or remove at front is better than the array, but insert back, remove back, get item, update item is worse than the array because we need to traverse through the list to access anything that's not at the front. Currently, our linked list implementation of the list, we only have one variable, which is the head of the linked list. If you remember our array implementation, we actually have the array and an integer variable called length that keeps track of the length. So what would be the time complexity of getting the length of our list? If it's our array implementation, it's O of 1 because you could just return that variable length. But if it's the linked list, it would be O of n because you have to traverse your whole list and count how many nodes there are just to return the length of your list. We can definitely do better. What if we just also include a variable length to our linked list implementation? Now we have something like this in our ADT where we increment length by 1 every time we add an element and decrement when we remove one. One more optimization we can do is improve the insert back operation. Currently, we have to traverse all the way to the last node so that we could link it to the new node created. However, what if we just add one more variable to help us? What do you think that is? The answer is to add another node pointer for the tail of the linked list. Now you don't need to traverse all the way to the last node because you already have a pointer that's there. So it will make the insert back a O of 1 operation. Let's compare the structure one last time between the array implementation and the linked list. So as you can see, the beauty of ADT is it provides the same interface but very different implementations. So far, we learned about 2 data structures that can implement the list ADT. Next, we will look into new ADTs, the stack and the queue. I'll see you then.